Okay, so here's where we were last time. We were talking about tangent planes. We were revisiting the question of tangent planes. We already know the equation of a tangent plane, but we took a different point of view, realizing that if you have a surface, if it is realized as a graph of a given function f, well, that's just how it happened to have been phrased. That exact same surface can be thought of instead as a level set. And this is a trick that we talked about, earlier in this chapter. That anytime you have something written as a graph, you can just kind of move things around a little bit, and now it's being viewed as a level set. Once you have it viewed as a level set, and you have this function of which it is a level set, well, then we know we can use the gradient as the normal vector, because after all, the gradient is always perpendicular to level sets, and the normal vector just needs to be a vector perpendicular to the surface. Okay, all right. So details. You gotta compute the corresponding gradient, and you gotta plug into the actual equation here and multiply things out. Blah blah blah. Details that I hope y'all will go through and follow through on. And the punchline is you get the graph of the linear approximation that we talked about long ago back in whatever section it is earlier in this chapter. Again, okay, so this is again a different point of view on how to get there. Okay, so picking up from there, let's see an example of that in action. So here's a function, and I'm apparently interested in the graph of that function, and I want to find the equation of the tangent plane. Okay, so, being a graph, right, this is what it means to be a graph of this function, right? And then, we pull the fast one here and, rewrite that as a level set by just, kind of moving things around a little bit. Realize now that we are talking about a level set of this function, and now that you have that function, we're in business. You take the gradient of that function, whose level set we're interested in, and that gradient is going to be your normal vector. Hey, you could play in the numbers, right? But there's the normal vector, and once you know your normal vector, you're basically in business. Of course, you do have to find an actual point. Right, so you got to find this point here that I claim we can use 2, 1, 4, because that's a point on the graph. I know it's a point on the graph because the first coordinates are the input values for the point that I've been given, and then the last coordinate, let's see here, the last coordinate is going to be what you get when you plug that into the function. And there's your x naught, and again, it's a matter of multiplying it out, and we're in business. Everybody happy? Okay. Now, I'm going to point out that even though this is just a reproduction of what we did on the previous page, it's arguably the exact same thing. And so we've used this strategy to find a tangent plane to a graph. It would be even easier, arguably, to find a tangent plane to an arbitrary level set. Because what we did here is we took our equation given as a graph, and the very first thing we did was rewrite it as a level set. If the equation you're given is already a level set, you don't even have to do that first step. If you're already looking at a level set of something, then, just take the gradient. Boom. Does that make sense to everybody? Okay. All right. Okay, all right, now here begins, this is a subtle topic that we're going to talk about here. It's the implicit function theorem and implicit differentiation. This is something you may have seen some of in high school calculus classes. It's, in my experience, almost never treated properly in high school calculus classes. And one of my big frustrations is that we're always in a hurry in this class, and as much as there are lots of beautiful and interesting mathematical considerations related to this, it is little bit more of an abstract discussion than it really than it is really ideal for Math 219, given the amount of time constraints that we have. So I'm going to hit highlights and try to give you some intuition for what the questions are that this worries about, and some sense for how we resolve those issues. And then we're going to get to the computations pretty quickly. So here's the big issue. Now, we just got through talking about an old fact. If you have a graph, you can always move things around and view it as a level set. So I want to go then to the opposite question. If you have a level set, can it be viewed as a graph? Now, we already know the answer is no. Or at least we know the answer is not necessarily. Right? But so when I have a level set, under what circumstances can I conclude that at least nearby, that my curve is a graph? Okay, so here's some examples. You see, we have a curve here, given by an equation. Notice written currently as a level set, and so. Question, can I view locally, nearby, can I view this curve as a graph? Okay, well, globally, absolutely not. This fails the vertical line test severely. Right? So globally, forget about it, game over. But what we mean by locally, and you look at this point over here, for example, locally, around that point, I say that this is a graph. Because by locally, what I mean is, if I just look just kind of nearby that point, forget about what's going on over there. That's too far away. But just nearby that point is that part of this curve a graph? And why, yes, it is. Right? Passes the vertical line test, no problem. Right? So locally, this curve is a graph near that point. Locally, and I emphasize the locally part, if I can get this to erase, there we go. Locally, near this point, the curve is a graph. Keyword locally, right? I'm not saying that for these values of x, that the original curve only gives you one value of y. That's obviously not true. But if I look only at the part of the curve that's near the given point, just that part of the curve only, that's a graph. Right? Because we're not including all that stuff there. It's too far away. So this is what we mean by locally here. Everybody on board? Okay. So this kind of thing right here, this sort of failure to be a graph because of the stuff that's way up above is not what we're interested in. When we say that sometimes we have even a local problem, we're talking about stuff like this. That point right there, if you look at the curve just nearby, right? I'm not talking about any of, we're throwing away all, that's the bad color choice. Let's see, let me do it like this. If we throw away all of that, and we throw away all of this, and look just at that little purple part of the curve, still fails the vertical line test, even locally, right? It hits twice. And furthermore, it doesn't even matter how little of the curve I look at. No matter how small I make my little neighborhood, it's always going to kind of, if you will, wrap under itself, because that point is exactly at the point where it's wrapping under itself, and you're going to have a vertical tangent line. A vertical line test problem. Does everybody see the problem? Okay, so who cares? The reason we care is because sometimes we want to be able to talk about derivatives, right? And so, for example, if I want to talk about, at this point, I want to talk about the tangent line, and I want to know the slope of the tangent line, wouldn't it be nice to be able to say, okay, well, near that point, and I don't really care. If I'm looking in this vicinity here, I really don't care what's going on over there. Right, I'm only interested in the tangent line at that one point. So reasonable to say, is it, good enough to say, is it locally a function? Because if it is locally a function, then I can talk about the derivative of whatever function that is, and I can say the derivative of whatever function that is is the slope. Right? So the problem is, if you're interested in understanding this part of the curve, it's not that the derivative of y is infinity or undefined. That's not the problem. The problem here is that at that point, near this point, it's not a graph in the first place. There is no function at all in any sense, even local. There is no function for which this is the graph. And so I can't even talk about a derivative, much less make claims about what the derivative would be if it was something I can compute. Right? So we're in this dangerous area where we might accidentally, in the hopes that such a function exists, start writing stuff down. But in fact, what we're writing down is meaningless garbage. And this is bad, right? That's not mathematical reasoning. Doesn't count. If what you're writing down inadvertently, you didn't realize it at the time, but what you wrote was meaningless garbage, you're not doing math. That's just not what math is. Does that make, I hope that's reasonable. Hope everybody gets that. Okay. All right. So before I claim that I'm looking at a graph locally, I have to establish that I actually am. So how do we establish that? And here's the big idea. Let's analyze the problems. This point here is a problem. Locally around that point, this curve is not a graph. I can't say derivative. I no, right? So what's happening here? What is indeed the problem? Well, the problem is that the curve wraps under itself. Right? It's the process of it wrapping under itself that's making it fail the vertical line test, because it wrapped under where it had been, and thus failure. Okay, so wrapping under itself. What is it that makes it possible for the curve to wrap under itself? I say that the fact that there's a vertical tangent line there is the problem. If a curve is at that very instant, that's where it begins to actually wrap under itself, it has to have a vertical tangent line. That makes sense, just a geometric appeal. Hope that's reasonable. Now, I emphasize, it's tempting to say, you're not allowed to talk about tangent lines because we don't know if it's a function yet. Not so. We can talk about tangent lines all we want. We just can't say derivative, right? Because this is not a function. Many things other than graphs have perfectly acceptable tangent lines. I have a vertical tangent line here. It's a perfectly good tangent line. It's just not to a graph, but it's still a tangent line. That's not a problem. Okay, well, now keeping in mind that our curve is given as, wrong thing. Our curve is given as a level set, right? It's a level set. And keeping in mind that gradients are always perpendicular to level sets. This is one of the things we established last time. If gradients are always perpendicular to level sets, then a vertical tangent line would mean a horizontal gradient vector. And if you think about it, horizontal gradient vector, and let's write down the formula for the gradient vector here. This gradient vector is partial f with respect to x, partial f with respect to y. Saying that it's horizontal means that this second component is 0. Everybody with me so far? So this is kind of the meat of it. There's this reasoning process gets us to the nice conclusion. If you have a problem, here, let me do it like this. If you have a problem, such as, for example, this, it follows that y partial would have to equal to 0. So problem implies this algebraic symptom. And then we have to recognize now that this is not useful as it's written. The whole point is I don't know if I have a problem. I need something that will tell me if I have a problem. And so we're going to do the contrapositive. I hope you all remember the contrapositive construction. The whole idea of a contrapositive is P implies Q. An equivalent way to say that is not Q. Well, then that implies not P. Right? Yeah.
Would y partial not equal 0 at an inflection point?
I don't know what that assumes we have a graph,
Okay.
which we don't know, and so yeah, right, yeah. Oh, no, I think I'm sorry, I understand your question now. I think what you're talking about is if the curve were to do something like that. Yeah. So at a point like this, yes, this is a graph, right? So I'm not saying that only problems will give rise to this symptom. But I'm saying all problems will give rise to that symptom. Does that make sense? Yeah. Okay, so contrapositive and all that, and our conclusion turns to this. I keep getting out of the right mode. If this algebraic event happens, if your y partial is non-zero, well, then again, contrapositive and all that, when this fails, then that fails. If the y partial is not 0, then you do not have a problem. Nothing like this is happening. Couldn't be. If something like that was happening, the y partial would have to be 0. So, no problem. So this is our test. This is what we call, in fact, the implicit function theorem. This is sort of a first cut at the implicit function theorem. Take the partial derivative of f. Let me say this more carefully. Take the partial derivative of the function whose level set you're looking at with respect to the variable that you want to be viewing as being a function. And not 0 implies no problem. And now you're in business. Now you can say, oh yeah, y is definitely a function of x, and go ahead and do your implicit differentiation, and it's all fine. Nothing bad's going to happen. You're good. Okay, so that's the single variable version, and here's the multivariable version. So now suppose we have an equation of 3 variables. Of course, an equation of 3 variables would be a surface in space, right? And can I view z as a function of x and y? Well, maybe. It depends. I mean, at a point like this point here, yeah, sure. On that surface, in the vicinity of that point, no problem. Passes the vertical line test. It's all good. But at a point like this one, where now the surface is in the process of wrapping under itself, right? We actually do have a problem there. So in the vicinity of that red point, this is not a graph. Certainly it's not, z as a function of x and y. And so I can't talk about, partial of z with respect to x. At this point, there is no such thing as the partial of z with respect to x because z is not a function of x. So, again, how do we detect these problems? And, well, again, the point is that it's wrapping under at that point, and if it's in the process of wrapping under, that means that we have a vertical tangent plane now, not a vertical tangent line. I don't know about the sort of the horizontal aspect of it. It could be sort of turned around in any direction. I don't know. But if it's in the process of wrapping under, then that tangent plane's got to be vertical. Right? And if it's vertical, then that means that its gradient, again, is horizontal. And if that gradient is horizontal, another way to say that is that its third component, namely the z partial, is 0. So again, notice slightly different picture, but strategically kind of the same, right? I mean, it's a lot of similarities in the argument. And notice again, what you need is to think about the partial with respect to the variable that you want to view as a function. In this case, I wanted to view z as being a function, and so it ended up being a partial with respect to z that we have to look at. And again, contrapositive and all that. Okay, so here is the final statement of the implicit function theorem. You'll notice now I'm going to state this for the n-dimensional case. So if this means I have a function of n different variables equaling 0. Said differently, I'm looking at an equation involving n variables. And of course, whenever you have an equation involving n variables, you can always take some of the terms and move them over to the other side. So all equations are level sets, etc. So in this most general case, if the partial with respect to a given variable is not 0, then you can view that variable locally as a function of the other variables. Okay. All right. So just for roll off the tongue purposes, always take the partial with respect to the variable that you want to view as a function. That's an important terse summary to make sure to remember. Okay, so for example, here's a surface, and by the way, I haven't got the slightest idea what this surface looks like. Right? No clue at all. Don't ask me to draw a picture of this. I can't. Yikes. Right? Okay. So I'm interested, though, in this point. It's not hard to confirm that point is on this surface. A little bit of arithmetic. So that's an actual point on this, whatever kind of surface that is. And near that point on this surface, can I view x as being locally a function? Well, again, whichever variable you want to view as a function, it is with respect to that variable that you take the partial derivative. What are you taking the partial derivative of? Well, whatever function you are taking a level set of. Now, again, it's got to be whatever you're viewing as a level set. Your thing is the level set of. So make sure you've got equals a constant. Might as well be 0, doesn't matter. But make sure you've got equals a constant on the other side. That is what you're taking the partial of. And you can compute that partial. You get this formula. You can plug in the point in question. Let's see, we're interested in at the point 1, 2, 3. So we plug in the point 1, 2, 3. And that value ends up being 4. And what do we conclude from the fact that it's 4? Well, 4, not 0. And not 0 means no problem. And yes, indeed, go ahead. Feel free to view x as a function of y and z. Go ahead and feel free to talk about the partials of x with respect to y and z. It's not meaningless garbage. We know for sure that x is a function. Everybody see how that works? Okay. All right. Okay, now a harder business, which is how do I then take the derivative? So let's see if I can squeeze this all. Okay. So how do I take a derivative of this new function? X is now a function. How do I take a derivative of it? I can't solve for it. All right, look up here. Can I solve for x in that equation? Oh my gosh, no. It's cubic. Nah, I can't, realistically. So, okay, if I can't solve for it, how am I going to take the derivative of it? And the idea is to make sure that you just, realize what roles each of the variables are playing at which stages, and then, roughly speaking, just go ahead and start taking derivatives. And I'm going to show you an example in just a moment. Keep in mind, though, what we're talking about is a situation where we're looking at a level set, right? I've already taken the partial with respect to the variable that I want to view as a function. I've already gotten not 0. I've already concluded that it is indeed a function, and you do have to do that part. I don't want to say it's the whole point, but it's a large part of what we're here for. Right? And now that I know that it's a function, I want to ask the question, what is its partial with respect to, let's say, a different variable, let's say xj. So I've got two pictures that that illustrate the roles that the different variables are playing here. I'm going to show you both of the pictures, but I'm only going to work with one. This is the sort of what you might call the full picture, but it's a little hairy, and it tends to freak students out a little bit. And so I'm not going to use this one. If you're interested, come by office hours. I'll be happy to walk you through it. It's ultimately very natural, and there's not that much really truly going on here. But here's the easier to understand. This is, I'm breaking some rules here. You know, I'm violating my rules about what types of diagrams are you allowed to draw. So, that's true. But at the same time, I'm gonna ask you to trust me that what we have here is, even though it kind of breaks that rule, it's still not going to lead to any problems, and this is a perfectly fine, sloppy, yes, but perfectly fine way to think about what we're doing here. Okay, so here's what we got. We've got this function that, don't forget, is equal to a constant. Right, there's our equation. In fact, I guess I left this as 0, so let's leave it as 0. So we've got f is equal to 0. And f is a function of all of these variables. Right? But now I want to view xi as being a function of all of the other variables, which is a little weird, right? But that's the whole the conclusion from the implicit function theorem is that I can view one of these variables as being a function of the others. Okay, and that said, now I want to take a partial of xi with respect to xj. Well, taking a partial of xi with respect to xj means xj gets to stay as a function, and I'm going to leave all the other variables constant. So all of that becomes that's a constant. Oh gosh, elbow again. That's a constant. All these variables in between are all constants. Everything's a constant except for xi and xj. So altogether, what we have is xj is a variable. xi is a function in terms of how it relates to xj, but it's a variable in terms of how it relates to f. So that's a little weird. You've got to keep track of the roles it's playing. Right? And everything else is a constant, and I don't have to think about them at all. So now let me clean up my picture. Actually, let me, not quite, let me leave it like this. Don't forget f is equal to a constant. Right? And I'm going to ask the question, as I change xj, how does capital F change? How does capital F change as xj changes? Well, there's two things I can say about that. On the one hand, as xj changes, that will directly lead to changes in f. Just in the sense that f is a function of, among other things, xj. But then there's also this little matter, and that is that as I change xj, well, xi now is a function of xj. So that's going to contribute a change. And then further, don't forget that as xi changes, that contributes to changes in f. Right? So there, in some sense, there's two things that happen. As xj changes, some changes go to f by directly, and some go by way of xi. But altogether, these are the only things that are changing. Everything else is constant. And furthermore, don't forget, the whole point to all of this is that f is constant. It's not allowed to change. The grand total change, all of these changes floating around in these two different directions, they have to cancel. They have to add up to 0 because f is not actually allowed in total to change at all. So these add up to 0. And keep in mind the goal, our question, what we were interested in here was how do I compute this partial derivative? Thinking of xi as a function of the other variables, how do I find the partial of xi with respect to xj? And you just solve in here. And what you get is, let's see here, it's this divided by that with a minus sign put in here because, well, algebra. How we doing? Everybody with me? Yes.
If we did like f equals c, some other constant, we would just put
Yeah, it doesn't make any difference because if this was, C, then again it remains f is constant, and so how does f change? Well, not at all. And so yeah, it doesn't make any difference at all. Yeah. Okay. So here's a formula, and I encourage y'all to remember this formula. It's a good one to memorize. All this stuff to erase. So yeah, make sure to remember this formula. Good news, bad news. Good news is it kind of looks like these sort of cancel. By the way, this is all math crime, right? Apologies in advance. Total nonsense I'm about to commit. But it's as if those cancel, and then the denominator of my denominator becomes my numerator, and it really kind of just looks like it should equal to that, except for this weird little minus sign here. And that's, again, just something you just have to remember it needs to be there. Right? It needs to be there because algebra. I mean, again, it unavoidably is there. So the good news is there's a nice little memory trick. Other than the minus sign, it looks like a cancellation. That will help you kind of reconstruct this formula as needed. That's the good news. The bad news is if you forget about that minus sign, then we have a massive, massive problem. Right? So this formula as written is correct, no problem, full credit, everybody's happy. But if you were to forget the minus sign, right, then this is, well, for one thing, it's wrong. But it's importantly wrong. It's wrong in the way that it makes it look like the student who wrote this actually believes that these cancel and that denominator of denominator moves. It makes it look like you think that these things are actually little objects that we're looking at fractions of, which is completely not true per earlier discussion, right? So the difference between the correct formula and the appearance of a complete misunderstanding of the subject, right? The difference between best possible and unacceptable is this one little minus sign. So don't forget that minus sign. I'm making a big deal out of it because I want to make sure that nobody forgets that minus sign. Yes?
Okay. And like single variable calculus, like
yeah.
You just have like a regular d.
Yeah.
Like, can you view that as like a differential?
It depends on the situation. If you're talking about in just taking an actual derivative dy dx from an implicit function, no, the minus sign needs to be here.
Oh, no, like in general.
Yeah.
Like
if you're talking about the chain rule, then yes, right? But it's. I can't give you any broad stroke, don't worry about it context. Yeah, I mean, you always have to make sure that what you're writing down is actually true and valid, and don't rely on, things that look the same must be the same. These two partial f's are not the same thing. They're just part of different scenarios, right? I mean, let me just remind you, partial f in the context of this numerator up here is a scenario where xj is a variable and xi is a constant. And then we have a completely different scenario down here. This partial f is involved in a story where xj is a constant now and xi is a variable. So they're just different. Does that make sense? Yeah. Okay, can't emphasize it enough. Don't forget that minus sign. Extremely, extremely important. Okay. All right, so let's C1. Let's look at this question here. Here, let me do this. You'll recognize that as the same equation above. In our earlier example, exact same equation. Still near the same point, and the question here, what is the partial derivative, this time of x with respect to z? There's something awkward about what I have circled, if what I had circled were the question. In this equation, I'm given no reason to believe that x can be thought of locally as a function. It's a variable in this equation. And yet, even though I've given you no reason to believe that it's a function, I'm asking you to take a derivative of it. And so your garbage warning should be blaring. What he's asking me to take a derivative. I don't know that this is a function. I'm not allowed to take derivatives of bicycles. I need to establish that this is a function before I go around doing with it what I do with functions. Right? Okay. Now you'll notice the way I have the thing actually phrased. I'm starting with a given that x is locally a function, and that I can take that as a given because I've already answered that question. Yes, x is locally a function. So, on an exam, if you were to see what I have circled in dark blue here, on an exam, if you see that dark blue, step one is you have to realize, it's part of your job, part of answering the question responsibly is to realize I have to first establish that x is locally a function. You'd have to do this part first. All right? Establish that it's locally a function, and then second part, you can then say, okay, well, here's the formula from the previous page. Again, don't forget the minus sign. But minus signs aside, it's an easy formula to remember because I get to pretend like these cancel. Again, I get the willies in explaining this part of it. But they don't actually cancel, right? But as a memory tool, it's fine to think of those as canceling and to think of this as being up there and thus there, and to make sense out of remembering this formula. That's okay. Don't forget the minus sign. Then I have a couple of partials to take, right? No sweat. This f is the function whose level set I'm looking at. So it's all that business. And this partial then is that. And this partial is this. And plug in the point that I'm interested in, and I'm interested in what's going on near that point right there. So we plug that in, and arithmetic, and done. What do you think? Everybody happy? Okay, so when you encounter a problem like this, it usually won't be phrased like the way I've got it phrased here in the notes, where I broke the question up into two separate questions. First question, is it locally a function? And then second question, given that it's locally a function, what is the partial derivative? I'm usually not going to break it into two questions. And by the way, not just in my exams, in life, right? In STEM life, as you're doing engineering questions, etc., you're going to find yourself looking at some equation like this, and it's not going to come with, oh, and by the way, we already know that such and such. Right? So when you see one of these questions, the first thing that you need to do is all of this business, right? That'd probably be, by the way, about half of the points for the question, is does the student realize that we need to establish that x is a function? Does the student realize what the appropriate partial derivative to take is? Does the student plug in correctly? Does the student realize that non-zero means cool, no problem? Right? There's a lot of thoughts in this part of the problem. That's probably about half of the points. And the other half of the points is then, correctly understanding how to compute the given partial. Don't forget this minus sign. Again, it's hard to overstate it. Right? Please don't forget the minus sign. And then algebra and arithmetic, etc. Everybody cool? Everybody on board? Okay, so that finishes chapter 2 for us. We're going to move on now to chapter 3. We've already done section 3.1. Remember that I felt it necessary to stick in 3.1 so that I could have, a convenient interpretation of derivatives of parametric curves for doing the chain rule. I like having that in my toolbox for that purpose. But now on with 3.2. So we're going to consider the question of how long is a parametric curve. All right, so I'm going to have to develop some machinery here. So temporarily, let's set that question aside and let's just consider, look, I've got a parametric curve here. And if I have a parametric curve, I can talk about the derivative of that parametric curve. And I hope it's unsurprising that if I know the derivative, then I can talk about dx being a linear approximation of displacement as being velocity times time. All right. So in fact, let me go ahead and do this. Dx is x prime dt. Everybody buy it, right? Or said differently, dx is equal to velocity times time. Displacement is velocity times time. Old news, I think. Okay, now let's talk then about this distance. Let's see here. I'm going to do this in green. That distance, ds, the distance along the curve, is a scalar. It's not the dx vector. Dx is a displacement, right? Displacements have directions. Displacements are vectors. Distance is not a vector. It's just a scalar. But I claim it's just the magnitude part of the dx. Right? If you know your displacement, or if you have a close approximation of your displacement vector, magnitude is the close approximation to the arc length. Is that cool? Okay. And then let's go ahead and also recognize that dx being v dt, I can view that as magnitude of velocity times time. Okay. All right. Now, these objects noted, let's now consider also, let's see, color choices. I'll use blue. This is an object of interest. It's what we call the unit tangent vector. And we're going to use this unit tangent vector in various different circumstances, most notably when we get into chapters 6 and 7. But this is a nice opportune moment to bring it up. It's, after all, we have a parametric curve, and we're moving along a parametric curve, and we're talking about the velocity and the displacement differential dx. The unit vector pointing in the direction we're going, yet another vector in that same direction. And how do I think about this? Well, you can think of it as, we know the velocity is pointing in the correct direction. Velocity goes in the direction the curve is going. So if I want the unit vector in the direction the curve is going, I just want the unit vector in the direction of the velocity. Is that all right? Okay, and with which of course you can write in either one of these ways, totally equivalent. So then I claim this gives us an alternative way to think about the dx vector. Claim you can think of the dx vector as being t times ds, and this is just a matter of kind of just noticing that if t, after all, is that. Right, that's what t is. And if ds is that, right, that's what ds is. Then you look at green times blue, this times that, and the magnitude of v cancels, and you get v dt, aka dx. So it just fits. Everybody with me? This is a different way to think about the dx vector. Okay, and now that's algebra. Here's a more intuitively satisfying explanation. Let's understand this vector. What direction does this vector point? TDS. What direction? Well, it points in the direction the curve is going. It points in the same direction as dx. What's the magnitude of this vector? Well, the magnitude of this vector, t is a unit vector, of course. So the magnitude of this is just, whatever ds is, it's the magnitude of dx. So this thing I have in purple points in the same direction as dx. It has the same magnitude as dx. It looks like a duck and quacks like a duck. So it's a duck. Is that cool? All right. Okay, so, all right, with all of this established, now you want to know the arc length of a parametric curve? Well, each little piece of parametric curve, ds, we have formulas for ds. I just need to add those up, right? Adding up over the entire curve means I'm just going to, well, take an integral. Everything's a function of time here, and adding all that up, this integral turns into that integral. After all, don't forget our ds is speed times dt. Everybody buying it? Okay. All right. So the trouble is these calculations are tedious. Tend to be, and so you end up with ugly integrals. So, for example, this integral, in the case of this example here, turns into this, right? And it's just, I mean, there's your parametric curve, and you can compute the velocity. The velocity is just the derivative of that parametric curve, so there's that velocity. And then taking the magnitude, okay, well, the magnitude is going to be the square root of the sum of the squares of that velocity, and you get this horrifying integral here. And it's not that it's not doable, but it's, actually, I'm not entirely sure. I wouldn't want to bet my life on being able to compute this integral. So it tends to come up, I mean, that these integrals are brutal. Very often, if I ask you to compute a length of a parametric curve, unless it has been carefully crafted so that a bunch of terms cancel, and under the radical you happen to have exactly a perfect square, and so the square root goes, unless something really nice like that happens, yeah, the question will be, leave your answer as an integral. Because they're hard. Okay, how's that sound? Okay, alright. So if you have a parametric curve, for example, here's a parametric curve. This parameterizes that parabola. Easy to check, right? You can just plug in what y is, plug in what x is, and boom, the equation works. So we've got a parameterization of that curve. Well, here's the thing. This thing right here is also a parameterization of that same curve. Because if you plug in for x, you plug in for y, the equation works. Right? So the punchline here is that any curve has a lot of parameterizations. Parameterizations are really, really, really not unique. And in fact, you can think of where, what relates these two parameterizations as, well, this equation relating t and q relates those two parametric curves. And so you could imagine that any kind of relationship that you write down where one of the parameters is a function of the others, and you probably want to worry about monotonicity and stuff. Let's not get into the weeds on that. But lots and lots of relationships that you can write down between the parameters will allow you effectively to turn one parameterization into another parameterization. So there is a special choice of this that is nice, and that goes as follows. If let's suppose we have a parametric curve parameterized in terms of t, so our favorite choice of parameter, right? Think of t as time. So I like to think of this, by the way, as a road trip. I like to think of I'm cruising along a road, and you give me a call at any moment in time t, and I will report my position x, and that road trip traces out this curve. That is a parametric curve. Okay, so I'm going to define now a new parameter based on t, and the new parameter is actually very simple to describe. The new parameter is what I'm going to call s. You can think of this as being, well, its arc length. In the road trip metaphor, s is just the mile markers on the side of the road. It's, how far are you away along that road from some, fixed reference point, whatever, where the downtown, I don't know, where do they put the 0 on mile markers? Is like the courthouse or something like that. Whatever. Doesn't matter. So, this also is a parameterization. You can look at, Google Maps or something, right? And, at some distance S away from the courthouse, you are at a location X, right? So we can think of X now, position, not as a function of time, but as a function of distance traveled. And I can relate these two parameters because this distance traveled, that arc length, right? We have a formula on the previous page. The arc length is just, that integral. And so we have a relationship between T and S. Is that cool? All right. Now let me talk about the notation in this integral, and I apologize for the annoyance. But note this integral goes from 0, which is where we started, to T, which is where we are at the moment where I want to compute that arc length. And I know that I need to chop that up into little pieces and add up all those little pieces. And the problem is I've already used T as one of my bounds. Right? If T is a bound defining the arc length that I want to compute, I cannot then also use T as the variable that sort of cruises along between 0 and T. Okay. So we come back up to this equation for arc length, and I just point out that the T in this equation, arbitrary. There's no reason why you have to use T. It's a dummy variable. You could use whatever you want. You can call it Q if you want. Whatever. So our book and a lot of books in a situation like this, in order to kind of maintain the convenient point of view of thinking of your parameter as being kind of like time, our book chooses the lowercase Greek letter tau because it looks kind of like a T. It's playing a role of kind of like a T. I just can't use T, and so that's why we have a tau here instead of a T. Is that cool? Y'all have a good day. See you later.